Okay. Thank you, Debbie. All right, perfect. So sometimes we want large motor units, like in big muscles. Think about your quads. I can have one nerve that supplies 200 muscle fibers, which means that I only have to send nerve impulses down that one nerve to stimulate 200 muscle fibers. So when the goal is brute force, if your goal is like force of contraction, you want large motor units where each nerve supplies hundreds of muscle fibers. Isn't that efficient? I can send a nerve impulse down one axon and it will stimulate 100. Whereas smaller muscles that control fine movements, think about the muscles of your face or your fingers. Here we want small motor units. So each axon might only supply 10 because the goal isn't so much force, it's control. You have more control when I can send a nerve impulse down that nerve, but not that one. I can send a nerve impulse down that nerve, this one, but not that one. In my quads, there's not a whole lot of control, right? So sometimes you want large motor units. It's efficient, so you can develop a lot of force. Big muscle groups. Other times you want a small motor unit, so you have more control. Now, these motor units are very rule bound. So within a motor unit, remember, we're talking about a nerve and however many muscle fibers those nerve endings supply. So let's just say we're talking about the red one. If we're talking about the red motor unit, the unit of this one red nerve and the 3 muscle fibers it supplies, it is an all or none proposition. Within that red motor unit, when I send a nerve impulse down here, all 3 contract or none contract at all. So within a motor unit, either all muscle fibers that it supplies contracts or none. You can't do 50-50 within a motor unit. All or none principle. If I send a nerve impulse down here, all 3 will contract or none. The second thing here is what I was referring to before in response to your question. Ashley. Yes, well, I don't know why, sorry. I was like Bartlett, but I want to get your first name. Yo, Bartlett, drop and give me 20. Like in the military, we call by our last name. Oh. So every little tiny nervous activity doesn't result in a contraction. So as a preview for the nervous system, not every activity in the neuron results in a contraction. We have some like minor level electrical activity all the time, but it's only when we send a nerve impulse and it reaches a certain threshold that it fires. That's good. We don't want every little nervous activity to give us a muscle contraction. More importantly, the bottom one. Every motor unit, every muscle fiber, I guess you could say it either way. Every motor unit or every muscle fiber contracts at the same intensity. I mean, folks, those actin and myosin slide together, and it's just, it contracts at a given intensity. That cannot change. So within the red motor unit, when this muscle fiber and this one, when they contract, it's the same intensity. Each muscle fiber is the same intensity. So the question is, how do I make an overall muscle contraction more or less intense? If I'm doing leg extensions and I'm trying to lift 20 pounds, that takes less force than if I'm trying to lift 100. So we are able to adjust the intensity of overall muscle contraction. How do we do that? By the number of motor units that we recruit. If I want to contract my quads as forcefully as possible, I'm going to activate every single motor neuron, every single motor unit. Let's use this as an example. If I want to contract this with maximal force, I will send nerve impulses down the red and the purple. So if I want to contract my quads with full intensity, I will activate every single motor unit. I will activate every single motor nerve. But if I'm only lifting a little, maybe I only activate 50 out of 100. If I only want to contract this muscle partially, maybe I only activate the red nerve, but not the blue. So each individual muscle fiber contracts with the same intensity, but I can change the overall intensity by how many nerves I stimulate, by how many motor units I stimulate.
Sit on it. You have the video. I'm gonna relax my forehead. But then I look unhappy. I am kind of tightly wound, it's true. So my family tells me.
Yeah.
What did my mom say?
That's what your mom said.
No. She said, your hair looks like that. She's in a nursing home, my mom. She thinks she works there, so she gets up every morning and she like checks on all the other people. It's cute, but she gives them a hard time. Like all these old women, she'll be like, "Are you up yet?" But it's like her way of cute.
Okay. Now, when we start to put it all together, I've already alluded to this. Now we're just applying names to it. Didn't I already say most of our muscle contractions are when we send multiple nerve impulses? So when I was saying that, let's just take an easy exercise, like a bicep curl, or writing, walking. Those are all what's considered a graded muscle response. All that means is we're sending multiple nerve impulses for a sustained contraction. A graded muscle response, all that means is we're sending multiple nerve impulses in order to get a smooth, sustained contraction. Pretty much everything we do is that way. We've got to send many, many nerve impulses to get that sustained contraction. We're sending many, many nerve impulses, and the result is a sustained contraction. The only other alternative is if we send one nerve impulse and we get only one cycle. That's a twitch. So a twitch is really just technically defined as we send one nerve impulse to a muscle and we have one cycle of events and that's it. One nerve impulse just means we get one little slide and we're done. Those cross bridge power stroke release doesn't repeat. Twitch is really just a protective thing, like best example of a muscle twitch. I mean, sometimes you felt a twitch, haven't you? But like if a bug comes near your eye or a speck of dust, you might just, it only might take one nerve impulse and one cycle to cause a root. So sometimes a twitch is enough, but most of our muscle activities are a graded muscle response, where we're sending multiple nerve impulses to get a sustained contraction, not just one and done. So there's a way in which we can talk about these graded muscle responses. In order to get a graded or sustained muscle, now we're looking only at this, okay? In order to get that sustained response, doesn't it all start with a twitch? Everything's. I do need to relax, Erica. Everything starts with that one nerve impulse and one contraction. But usually we want a sustained contraction. So if you look at this graph, this S means stimulus. What's the stimulus that goes into a muscle to tell it to contract? The nerve impulse, right? So if we look at this graph, it's trying to show us if we send one stimulus or one nerve impulse, tension means the muscle's contracting. If we send one nerve impulse, we'll get one contraction and we're done. That's a twitch. But if we want to have a sustained contraction, we will start to send repeated nerve impulses. That's what I said, right? Most of the time, we have to send multiple nerve impulses to get that sustained contraction. Well, when we start to send repeated nerve impulses, they begin to summate. And that means that the effects add on to each other. So we send one nerve impulse, contract, relax. But when we start to send more and more, we start sending an additional nerve impulse before the muscle had a chance to relax from the previous one. So we start to send stimuli, we start to send nerve impulses so quick that the effects summate. Look, here's a nerve impulse, muscle contraction. It doesn't have a chance to relax before we send another one. So the effects begin to summate. They add on to each other. Then we start to send nerve impulses so quickly that we get what's called incomplete tetanus, like a quivering contraction. But ultimately, we send nerve impulses so quickly that we reach that smooth, sustained contraction, which in this way is called complete tetanus. You don't realize this is happening, because by the time we get to that sustained contraction, we've already gone through these. You don't realize it happens so quick. I encourage you to not delve into that. Don't make it more difficult than it needs to be. We just started with muscles, skeletal muscles can contract in two ways. If we send one nerve impulse, there's one contraction and we're done. That's a twitch. Your eyes twitching for protection. But most of our muscle contractions are sustained, which means that we have to send repeated nerve impulses. When we do that, when we send repeated nerve impulses, the stimuli begins to summate, add on to each other. And we go through these steps, know the order of these steps, right? Twitch, summation, incomplete tetanus, tetanus. When we get to that sustained, smooth contraction. Got it? Got it. Yes. Yes. Let's see here. All right, so we're actually done with the bulk of this chapter. What's left is some odds and ends.
So our summation, incomplete tetanus, graded muscle response, all three of them.
Those are the steps in order to get to a graded muscle response. Her question was, summation, incomplete tetanus, and tetanus. These are the 4 steps in order to get to that graded muscle response, that sustained contraction. In order to get to that sustained contraction, we have to go through twitch, summation, incomplete tetanus, and tetanus. Okay, ready for some odds and ends? The potpourri, shall I say? The potpourri. I'm just gonna give you these statements, and these are just like little added statements. We talked about those motor units. We tend to recruit smaller ones first and then larger ones. That's it. Even with the quads, like as you're getting going, your nervous system automatically just first sends nerve impulses down the smaller motor units, and then it gets its way working up to the larger ones. This is evidence of why it's good as an athlete to do a warm-up. You know this, if you're at the gym and you're trying to lift your heaviest weight, is it gonna be on the very first attempt? When you're like cold? Probably not. So one physiological explanation for that is that we know that we're first gonna recruit small ones. So if we really wanna get to those strong motor units, I shouldn't say that. If you wanna get the most forceful contraction, you wanna do repeated ones so you can get to those larger ones. All the rest here is extra. We just recruit smaller ones first and then larger. This is along a similar vein. There's this thing called the Trepp effect. All we're saying is, when you do repeated muscle contractions, they get stronger over time. Which is to say, your very first contractions are weaker. More evidence for warming up as an athlete. Your initial muscle contractions are a little weaker. First of all, we have only recruited the small motor units to begin with. But another reason is this. This has to do with the availability of calcium. Your first couple of muscle contractions, you just don't have as much calcium available. But as you do a couple more sets to warm up, your body's going to make more calcium available. And guess what? With more calcium, I can do more cross bridging and more contraction. The Trepp effect simply states that our initial first contractions are weaker, but successive ones can get stronger because we have more calcium available. Our first initial contractions are weaker, but as we continue to do a couple more, they can be stronger because we're gonna have more calcium available.
Do you love physiology? Maybe not yet.
So all I want to point out here, there are so many ingredients needed for a muscle contraction. What are some of the ingredients we've already gone through? We know that in order for a muscle to contract, we need a nerve impulse. We need acetylcholine to cross the synapse. We need calcium. We need ATP. We need all these ingredients. Well, what we haven't talked about yet is how we get that ATP for the myosin head. In order for the myosin head to have that stored energy, ATP, remember, isn't ATP that usable energy? What do we convert into ATP? Glucose. So all I'm pointing out here is where do we get that ATP? We have to take that glucose and convert it into ATP. Back up for a second. In order for a muscle to contract, doesn't it need fuel? Our muscles can burn glucose or fat, right? So I'm just introducing the fuel. Like for a car to go, it needs gas in the tank, doesn't it? So in addition to the nerve impulse and the neurotransmitter acetylcholine and the calcium, we also need fuel, energy. This is how we generate that ATP. If you wanted me to be a little bit more clear, how do you like that? This is talking about, we know that the myosin head stores energy. Well, how do we get that energy to the myosin? All you have to know is we have 3 energy systems. Just know them in order, which is to say, what do our muscles use first to generate ATP? Something called the creatine phosphate. What do our muscles go to second? Something called the anaerobic glycolysis. What do they go to third? Something called aerobic. Your exams are multiple choice. All I want you to know is these in order. 1, 2, 3. These are the chemical pathways of how we generate ATP for that myosin head. These are the chemical pathways for how we generate ATP for the myosin head. The first 2 are anaerobic. What does that mean? Anaerobic means it doesn't require oxygen. That's yet another ingredient we need for muscle contraction, oxygen. But we need our muscles to be able to contract quickly. So the first 2 don't take oxygen. That means that we can generate We can generate ATP long enough to contract a muscle for about a minute or so without oxygen. But then if we're gonna continue sustaining that contraction, we need oxygen. Just be able to put these in water. I don't want you to focus on this too much. I'm just another ingredient. All the rest here is extra. Be able to put them in order. Creatine phosphate energy system, anaerobic, and then aerobic. Be able to put them in order. Creatine phosphate, anaerobic, and aerobic. I almost did a sister, Mary Gallagher from SNL, who goes like this. You ever see that? It's like more. Okay. Again, I'm just throwing at you some tidbits here and there. This is going to make sense when I explain it to you very simply. The length tension relationship. If I was to look at my biceps brachii, at what range of motion can my biceps brachii contract with the most force? Could you lift the most weight when you're fully extended? Could you lift the most weight in mid-range? Or could you lift the most weight from here to here? Where are my weightlifters? That's it. Last workout session. I'll just tell you. So what this is telling us is our muscles can generate the most force in mid-range. I mean, if I try and generate force from here to here, I can generate some, but not as much as here. Your muscles can generate the most force in mid-range. It has to do with the actin and myosin. When I'm fully extended, think of the actin and myosin in my biceps brachii. They're farther apart. So you can't generate as much force out here because the actin and myosin are farther apart and have a little more work to do to walk together. When I'm here, the actin and myosin are already overlapped quite a bit, and there's not much more for them to go. So when you're in mid-range, your actin and myosin are not too far apart, not too close together. In mid-range of a particular joint motion, the actin and myosin are not too far apart, not too close together. You can generate the most force in mid-range. That's the best way to think about this. And these pictures are trying to show you that. If I'm flexed too much already, the actin and myosin are already overlapped. They don't have as far to go. If I'm extended too much, the actin and myosin are farther apart. And it just takes a little bit more work to bring them together. You can generate the most muscle force in mid-range because the actin and myosin are not too far apart. They're not too close together. They're just right. I'm going to skip a lot of slides. Are you ready to cross some things off? Don't worry about the muscle fatigue. Don't worry about endurance or max VO2. But we are going to talk about this. We're almost done, folks. I know it's been a long night. Next week won't be as long. I can answer the questions. Let's go way back to our anatomy. You know, back when you were not so tired of being here. We had the whole muscle, the fascicles. Each fascicle is made up of muscle fibers. Well, it turns out these muscle fibers can be a little bit different. There's a type 1 muscle fiber, otherwise known as slow twitch. And there's a type 2 muscle fiber, otherwise known as fast twitch. They're similarly structured, just slight alterations. A slow twitch muscle fiber is more geared for lower intensity contractions. Look at the bottom bullet point. Longer lasting contractions, but weaker. I would just go with that bottom bullet point. A slow twitch or type 1 muscle fiber can stay contracted for longer, but it's a weaker overall contraction. A type 1 or slow twitch muscle is what a marathon runner would rely more on. It contracts weaker overall, but can stay contracted for longer. On the other hand, the opposite, a fast twitch muscle fiber is a little bit more geared towards strong contractions, but if they're stronger, they can't stay contracted as long. A sprinter is going to be utilizing more of their type 2 fast twitch. Strong contractions, but it cannot stay contracted for as long. You ultimately have both. Every muscle is a combination of both. But through training, how does an athlete get faster? They work on they train, and over time, they're able to activate more fast twitch. This is one explanation of the adaptation of training. Look, here's a cross section of a muscle. These are the muscle fibers. They put stain in here. The slow twitch are the type 1, they stain darker. I'm not going to ask you this, but this just shows you that every muscle has both. In this picture, the slow twitch are the darker ones, the fast twitch are the lighter ones. This is the end, folks. This is the end. Here we go. We've spent all this time focusing on skeletal. Now I want to go back for a short compare and contrast. I have put stars beside what you need to know. When we're looking at the structure of skeletal versus cardiac muscle, there's some slight differences that are very similar. Here's what I want to point out this evening. Structurally, cardiac muscle cells, muscle fibers, have more mitochondria. Wow. Isn't that a beneficial adaptation? Cardiac muscle has to contract all the time. So doesn't it need more mitochondria? Which part of the cell produces energy? Mitochondria. Back to chapter 3, folks. You don't have to know these percentages, but skeletal and cardiac muscle are very similar. One small difference is that the cardiac muscle has more mitochondria. Here are some functional differences. You only need to know the lines here that are starred. I mean, you already know that skeletal muscle is voluntarily controlled and cardiac is involuntary. Compared to each other, compared to each other, cardiac muscle is at a lower intensity. I'm not saying it's not forceful for what it is. But if I contract the myocardium, my heart muscle, to my quads, which can contract more powerfully? My quads. So skeletal muscle has the ability to contract overall with more force. Cardiac muscle comparatively contracts at a lower intensity. But of course, because of it having more mitochondria, can't the cardiac muscle contract for longer? Yes. Look at this bottom one. Skeletal muscle from the time of nerve impulse to contraction is quick. Skeletal muscle from the time of nerve impulse getting to the muscle to mechanical contraction is quick. 2 milliseconds. You don't have to know that, but just know it's quick. Cardiac muscle takes a little bit longer. From the time of nerve impulse to contraction, cardiac muscle just takes a little bit longer. It's fine. It's like kind of low and slow. Remember, what's the overall goal of skeletal muscle? Protection. These skeletal muscles are really designed to let us run away from the bear in the woods. Protection. Quick, but not long lasting. Cardiac muscle is more designed to pump out blood every day, all day. A little preview of what's to come in A&P2. There is a very small amount of cardiac muscle tissue that is called autorhythmic. And what that means is there's a small amount of cardiac muscle tissue that can contract on its own. You've heard of the SA node, haven't you? That is an example of autorhythmic contraction in the heart. We'll talk about it more in A&P2. That's only possible in cardiac muscle, where it doesn't have to have the traditional nerve impulse from the brain. Only about 1% of the myocardium in the heart is autorhythmic. But that is only a characteristic of cardiac. Most of the cardiac muscle is just like skeletal. But look, I just gave you that number, 1%. It's only a small percentage of that cardiac muscle that can contract autorhythmically. Last 2 thoughts for the evening, and then I'll check the answer key. No. This is just more information. All you need to know is something that's unique in the cardiac muscle is a small percentage of the cardiac muscle can contract autorhythmically. I have 2 comments about smooth muscle. Overall, skeletal and cardiac are very similar. Overall, skeletal and cardiac muscle are very similar. Smooth muscle is a little bit different. Let me give you 2 comments about smooth muscle. Its structure is different. That's my general comment number 1. My general comment number 1 about smooth muscle is that its structure is a little bit different. Here are some examples. It doesn't have the same neuromuscular junction. It doesn't have the striations. It has a different ratio of myofilaments, blah, blah, blah. The general comment number 1 is that the structure of smooth muscle differs from skeletal and cardiac. Skeletal and cardiac have the muscle fibers, the myofilaments, the myofibril. Smooth muscle structure is different. The second general comment about smooth muscle. The second and final comment for today's lecture about smooth muscle here. In skeletal and cardiac, we talked about the sliding filaments this way, right? In skeletal and cardiac muscle, the myofilaments slide past each other kind of horizontally. I like this picture because it gives you an idea. In smooth muscle, instead of a contraction just happening in a purely horizontal, the contraction of skeletal muscle is almost like wringing out a wet rag. So instead of it just being like a linear shortening, the myofilaments kind of look like a lattice work, don't they? For grill marks on a steak. So when smooth muscle contracts, it kind of twists. That's my second comment. It contracts in a different way. It almost like, how would you describe that? Twists. Like wringing out a wet rag. Like a worm shriveling in the rain. Relax at the top, contracted at the bottom. Study hard.